Very good evening to you all, and of course, good morning to the people who joined from United States. And let me take an privilege to an honor to welcome Professor Perera on behalf of the IEEE Photonics Society Student Branch Chapter, Indian Institute of Technology, BHU Varanasi. And with this, I would like to welcome all participants who already joined, who are about to join, and who will not join. Anyway, so with this, we have another honor to have Professor Satyabrata Jeet, was a previous professor and previous head of the department in electronics engineering at IIT BHU, with us as a chief guest. So with this, I would like to request first, let's start this way. Let's invite Professor Bhattacharya from IEEE MTT Society faculty advisor, who can give us some small idea, like what is the student activity over here from the IEEE branch. Yes, Dr. Bhattacharya.
Okay, so good evening to all the delegates who are joining from India, and good morning to all of you who are from US. So I, on behalf of IEEE MTT Society Student Branch Chapter, IIT BHU Varanasi, welcome you all for this event organized by IEEE MTT Student Branch Chapter jointly with IEEE Photonics Society Student Branch Chapter. So we, in this particular era of pandemics and this worldwide pandemic situation, we are organizing a few webinars which are going to be delivered by all the distinguished fellows. Okay, so in fact, just I believe that something around 20 days earlier, we had a beautiful webinar delivered by Professor P.K. Basu from Calcutta University under the banner of the IEEE Photonics Society Student Branch Chapter and IEEE Varanasi Subcenter. So welcome you all, and I am just handing it back to you, Dr. Das.
Okay, so before start, let us give us a handful of thanks to all organizer and executive committee members as well as IEEE. For this, I would like to request Mr. Sambit Kumar Ghosh, Secretary, IEEE Photonics Society, so just give us a vote of thanks. And after that, I will request Professor Jeet. So, Sambit, please.
Thank you, Professor Jeet, for introducing me. So, first of all, I would like to thank to the IEEE Photonics Society for supporting all of our student branch chapter activities here at IIT BHU premises. I would like to thank our distinguished speaker, Professor A.G. Unil Perera, for accepting a request for delivering an IEEE distinguished lecture. We believe this talk would have been very helpful for the students as well as faculty members working in this domain. It is a great honor to have Professor S.G. as chief guest for this program. Thanking you, sir. And also, we would like to thank IEEE MTT Society, SBC IIT BHU chapter for their joining hands for this program. This event wouldn't have been successful without the organizing committee members of IEEE Photonics Society, SBC IIT BHU chapter, and we are highly grateful to all our executive body members as well as general members. And of course, must thank you to all the participants who registered and present here for paying their attention and learning. I hope you would have got the best out of this webinar. That's all from my side. Over to you, Professor Das.
Thank you so much, Mr. Ghosh. So I would like to now request Professor Jeet to say us something for this event, and of course, followed by, please introduce our distinguished speaker, Professor Perera, to the audience.
Okay, thank you, Dr. Das, and thank you, Professor Perera, also for accepting our request for delivering this lecture here. So, actually, as you know that, I mean, there is no academic activities these days, physical programs. So that is why the webinar is the only way to interact and have some presentations and etc. So with these few words, actually, the societies are working in these directions. And some young guys, I like Dr. Shantanu Das, Somok Bhattacharya, and some other students members also there. So they are actively participating in these things. So now I would like to introduce Professor Perera. it's my proud privilege to introduce Professor Perera as my postdoc mentor also. And I have also learned a lot of things from his lab. So we had a very good group there at that time. So Professor Perera has earned his BS degree in physics from the University of Colombo, Sri Lanka in 1981, winning Justin Samarasekara Award for the most outstanding student of the year. Then he came to US and he earned his PhD degree from the University of Pittsburgh in 1987. And then he moved to the Georgia State University, Atlanta, US, as a faculty member, and where he is currently working as the Regents Professor in Physics, which is the highest academic rank in the university system of Georgia. And he has also won a number of, most university awards there, including Outstanding Faculty Scholarship Award, Outstanding Faculty Achievement Award, and Alumni Distinguished Professor Award. And his research interests at present mainly includes minimally invasive disease diagnostics using infrared radiation. In fact, he's a pioneer person in the area of infrared photodetectors, and even THz photodetectors also. That is also a far infrared region. So he's a very well-known personality that is in this area. So he has published more than 200 peer-reviewed papers in very reputed journals, mostly in the applied physics letters. That is, and although many other journals are there, but more than 100 publications, I think, so that is applied physics letters. And he also contributed more than 10 book chapters and more than 10 US and international patents. So he's the prestigious fellow of the American Physical Society. He's a life fellow, and Professor Perera also is the fellow of IEEE USA, and also fellow of the Society of Photo Instrumentation Engineers, that is SPI USA. So he's an editor of the IEEE Journal of Electron Device Society, and he is also recognized as the IEEE Photonics Society Distinguished Lecturer for the year 2020-2021. So with these few words, I would like to request Professor Perera to kindly deliver his talk on the topics optoelectronics, history of electronics leading to infrared detectors and applications. So please, sir, you just continue and start your lecture.
Thank you. Thank you, Jit, for the nice introduction, and I'll try to live up to that, but I may not. But in addition to Jit being my postdoc long time ago, I had one of his students as opposed to Divya Somwansi. I think she was in Israel, and now I think she's back in India. I forgot where she is. So, and I have visited IIT. I mean, those days it was Varanasi, BHU. So thanks for that invitation too. But so let me thank Professor Das for inviting me, and for Professor Bhattacharya to host as a distinguished lecturer, and for the society. So let me start my discussion. So as Jit mentioned, now I'm more interested in this minimally invasive diagnostics, but I will start from basic electronics development and give some applications, and try to briefly show some of the new results about minimally invasive diagnostics. And maybe some of the initial results, some of the faculty members and seniors may have seen that. So please bear with me for some time, because this is a student chapter. I thought that it's good to have some history given to the students. So this is the acknowledgement page. So I am listing only the two present students, but there is a whole group of earlier students, and I think JIT knows some of those people.
Yeah.
With
Yes,
those
Krishna. Yeah.
people, yeah, without those students, I would not be talking about anything, because most of the work is coming from students' work, and also the support from the agencies and my collaborators. And if you look at our papers, you will see most of the papers have some outside collaborator. When we were doing detectors, our samples were grown and processed at different places. And we come up with the design of the structure based on physics principles, and give the design to somebody and ask them to grow using MBE or MOCVD, and then get the device back, test the results, and do iterative improvements. And even the new research we do, we get so far the samples, the blood samples were from our collaborators, biology research faculty members at GSU. So let me start saying, I know you guys are engineering, but I want to give this idea about what is physics doing in your life. And maybe some of the engineering students might be thinking physics is not useful. But before the engineers do things, some physicists or even the engineers needs to think about basic physics principles and come up with the devices. So the picture you see, alarm clock. When you wake up in the morning, the alarm clock, now you can have a even much smaller alarm clocks than this, which tell you the temperature, humidity, the weather report, and everything else is there on that. Even with you can have an internet connection to this, and also have all the other reports you want about that. So now, after you brush your teeth and you can have your coffee ready, you can program your coffee machine so that by the time you come down, your coffee is ready. And then let's say that you are driving to a new place which you don't have directions. Your GPS will take you there. And you are driving with in a car or a motor vehicle. The car is driven, the safety depends on how fast you take the curves and what you do, and friction and all that is physics. So even the basic electronics has a lot of physics. I will get to that in a minute. And now even these presentations, now this is possible that I can talk to you in Varanasi from Atlanta, and you can hear me within less than a minute, and you can see this and imagine what would have happened without this capability in this time of this pandemic. But presentations, laser pointers, all these things, and calculators, everything else, microwaves, when you want to take the lunch, that the microwave will heat the part, the food stuff which has the moisture, because the microwave absorbs moisture, and it is not going to heat everything else first. It will heat the component which you really need to heat first. So that is saving time. And the new cars can be solar, and we already have Tesla and Leaf and other electric vehicles, and the superconductivity, maglev train, all those things are using physics principles. So even if you are sitting in a chair and getting up, that requires some physics, but you don't think about that when you do that. You are trying to push the ground when you walk up front. So that is physics too. So you don't pay attention to what is the day-to-day physics you are using, but it is very useful. So electronics, so the phones and all that, has physics in that. So this is the reason why the physics is very important even for engineering people. So this is a brief outline of my talk. So I will show some pictures about the applications coming from the starting from the development of electronics, and we'll show you some simple slides for our detector development, and then go to some applications trying to show the disease diagnostics, the beginning of that. So let's give you a history of how the development of infrared detectors. The very first infrared detector was not known as an infrared detector, but it was a thermopile in 1835. And then Willoughby Smith in 1873 detected the photoconductivity of selenium. That was extremely important development until very recently. And now that is not extremely heavily used these days, because now we don't use photocopiers much. So you should be able to guess what is the importance of the photoconductivity of selenium. Uh, you probably have heard about the Xerox machine. Xerox was the famous company name who produced the photocopiers. That is why it is called Xeroxing. But lately there were a lot of other companies who came into that. So the photocopier has a drum which is made out of selenium, and when the lights hits that drum, that conductivity gives rise to charges, and that is the reason the carbon particles get attracted to that, and that is how you get a copy of the letter or something you are trying to copy. So without the selenium photoconductivity, you would not have photocopy. And imagine how would you feel if you cannot do any photocopying before. I mean, now it is not that critical because now it has moved forward. And PN junction was the very beginning of the whole electronic revolution. So 1940, PN junction was discovered, and 1958, right after the World War, Second World War, the UK started the Royal Radar establishment in Melbourne. Now the name has changed to Kinetic. So they started the mercury cadmium telluride detector development. And it is still a very important material, but now there are other materials which is used for other type of device detectors. So the first infrared handbook came in 65, and the US Army Night Vision Lab, so 1965, the US dedicated the research lab, which is called the Night Vision Lab, now called Electronic Sensors Directorate, purely focused on infrared detector development, nothing else. And in 1968, Willard Boyle and George Smith worked on CCD, charge coupled devices, at Bell Labs. And at that time, Bell Labs was a monopoly, AT&T Bell Labs. All the phone company, there was one phone company in US, AT&T Bell Labs. All over US, it was the only phone company. They had enough money. They had their AT&T Bell Labs, a research arm of that. The scientists there had very much freedom to do whatever they want, as long as they can justify that it is useful for the phone. So when these two started CCD, the Bell Labs asked them, so what is the CCD? What is that going to do for a phone? And they said, this is the thing which is needed to have a camera in a phone, so that you can use a camera in a phone. So at the time, there was not much of a discussion about the cell phones as we know now. But the Bell Lab said that is fine. go ahead, and now you know the rest of the story. So 1947, the beginning of the transistor. So this is again Shockley, Bardeen, and Bratton. They invented the first transistor. So this is the PNP or NPN transistor, and this is the part which got the Nobel Prize. Not a nice package. So this is what physicists do. But this is not going to go like this into a device. So the engineers are the ones who will try to reduce the size and put it into a package so it can be into some setup where you can come up with multiple units and all that. So this is the beginning of the history of electronics revolution. And after the first transistor, Texas Instruments came up with the first IC circuit. So this is 2 transistors. So this is the beginning of the IC circuits, 2 transistors here. And another little more transistors, again Texas Instruments. So this is more than 2 transistors. And in 1992, the first 486 chip, Intel DX2, which had 1.2 million transistors. And when I joined my PhD research, our group had a IBM PC XT, which had a hard drive of 10 megabytes, not gigabytes, megabytes. And then a few years later, we had the 286, which had 20 megabytes. Then Compaq came up with something called 386. That was little better. So that until that time, we only had very large computers in some other place, and you connect it with the phone to the computer. So this 486 chip, Intel came up with 1.2 million transistors. In 2004, Pentium, which had 125 million transistors. And 2006, Intel Core 2 Duo, 291 million transistors. 2010, Core i7. So this one had 1,170 million transistors in this i7 chip. 2012, Intel Ivy Bridge, 1.4 billion transistors. But the chip size is not that different. Almost the same size, but the number of transistors are going up. So is there any use with infrared detectors for this transistor development? Yes. If you have a good working transistor chip IC circuit, your heat dissipation should be expected in the areas where the processors are. So you can test whether the processors are working fine, and you can see here the dual core processor, that there are 2 processors in that. So the looking at the heat pattern, the engineers can see whether there is some shorts in the circuit. So you don't have to damage the chip to check each one, because if you open it up, the chip, and damage it, then there is no way you can sell that. So the Intel founder, Gordon Moore, in 1965 said that the number of transistors on a chip roughly doubles every 2 years. And this is the straight line, which shows the time and the number of transistors. So this curve is showing roughly doubling the size. And in 2005, Moore said that, yes, I gave that statement, but I did not think that it is going to go this long. Why? Because that when this happens, you mean to increase the number of transistors in the given space, you have to pack more and more transistors together. So the distance between the contacts will be smaller and smaller. what happens if you have very high voltages in very close gaps? You will have breakdown. That means you have a spark. And I'm sure all of you have seen very high powerful breakdowns. Can anybody think about any of those breakdowns? If you cannot, ask me as a question, I'll tell you. And if you think you haven't seen any of these very high breakdowns, I will be surprised, but we'll talk about that as a question answer. So how are you going to get rid of this problem? Because you cannot go unlimitedly increasing this number. So this is a problem people are trying to address. So quantum computers, that is one area, and another group, Bell Labs and others, are trying to try another digit instead of 0 and 1 to come up with the middle half, so that instead of logic 0 and 1, to introduce another additional representation of half. So these are couple of different patterns which people are trying to overcome this issue. So the discovery of infrared was an accident. So as a researcher, and the one thing I think it's important to keep in mind is, when you see a result, if that is not something you expect, don't just throw it out. Just look at that and try to understand, does that make sense, or is that my mistake? Yes, half of or more than half of the time it may be a mistake, but there may be some percentages of the time it is not a mistake, it is some real result, but we haven't understood what is that. If you try to understand that, you will discover something. Several of our papers, patents, are those type of unexpected results. So Sir Frederick Herschel Williams, he was an astronomer, a musician, and discovered the planet Uranus. And he was trying to see what part of the light which you can see, the colors in the rainbow, which one has more energy. So he put some thermometers at different colors using a prism to break the light into different colors. And he had some extra thermometers left outside the red where he cannot see any light. But when he came back, he noticed those thermometers also show some indication that it has absorbed some energy. So rather than saying, oh, I don't want to think about that, that is a mistake, he was thinking, how come? Then he repeated itself, the measurement. So that is another important thing in research, repeat. And somebody else needs to be able to repeat your results too. So when he repeated that and get the same measurement, he realized that there should be some energy there. So he said that that is what is called infra. Infra in Latin is pre. So that is why beyond red is infrared. So that is the discovery of infrared. So this is the ENM spectrum, which shows the wavelength in meters and the size of that particular wavelength and the name given. So the wavelength in meters, so you can see this period is like 10 to the minus 3 meters. So this is a water droplet, and the longer the wavelength is, shorter the smaller the frequency, because they are inversely related. And so now this is the nanoscale region in this here protein and water molecule in between those. And now you can see the screen where you see the visible light, which is a very small region of the electromagnetic spectrum. And infrared can be categorized into various groups, short wave, mid wave, long wave, like that. And there are two interesting windows, two atmospheric windows, 3 to 5 and 8 to 14. why are they called atmospheric windows? The infrared gets absorbed by moisture and carbon dioxide. And these two regions have very low absorption due to CO2 and moisture. So if you are doing some measurements in the atmosphere, these two regions are the two regions which you should work in, because the absorption will be less. Otherwise, you will not have much of the transmission through this atmosphere. So the infrared detectors can be categorized to two groups, thermal and photon detectors, and you should be able to see what is the difference between thermal and photon by looking at the picture. So thermal can be bolometric, thermoelectric, or pyroelectric, and photon can be a photoconductive, photovoltaic, or photoemissive. So the main two are photoconductive and photovoltaic. Photoconductive means when you have light incident on the sample, there is a current going through. So due to the photons, there is conduction. That is the photoconductive. Photovoltaic means due to the light, there is a voltage drop. So the solar cell is going to do a photovoltaic, because when visible light hits, it comes up with a voltage, and that is how we convert that into a solar cell. So the thermal detectors are so these thermal detectors are slow compared to the photon, because the photon detectors work based on a transition between two energy levels, which is an electronic transition, either an electron or a hole. So they are very fast, absorb the energy and move to the other level. But thermal detectors will absorb energy and heat the whole material. So that is why it is a little slow. And we have worked with various type of detectors, heterojunction and split off band detectors. So these quantum dots, dot in well, tunneling keyword quantum dots, superlattice quantum dots, quantum rings, quantum wires, all these things, most of these things are very common. A lot of other people have worked on that, but some of these other ones are our own structure. So we have patents on that. We have done multi-band and polarization sensitive detectors, and then applications using these detectors. So let me show you some pictures. So this is a picture which is taken with a visible light close to the evening. Take a look at that and see what you can see. Now I'm going to show you the same picture with infrared. Look at these two birds, a cat and a cyclist, and this dog. Those were not very clear. And so you can clearly see the flame both in visible and infrared and the headlight, but other things are much clearer in this infrared image. So you can see the visible image and the infrared image. Here you can see a carcinoma, a cancer, a growth, fast growth. A fast growth means it needs more blood, so there is some heat signature because of that. And now these days people are studying most of the body parts, trying to see various different diseases using infrared imaging. And commercial application, the thermal analysis of a tank, the fluid level. You can measure the fluid level by using infrared. So this emissivity of the material also play a part in the detection of this level. And when there is fluid inside, the emissivity changes. So that is one reason for that. And this is a heat signature in a power line. So this indicates that there is a short here. So that means the power company needs to fix this. Otherwise, their power loss is not going to generate any money for them, because it is not dissipating in your house. it is dissipating outside. And if you put your fingers in a cold and hot water bucket and check with the infrared camera, you can see the difference between the two. So this is another commercial application in cold places. Winter here, leaks from the house. The windows are common infrared heat leaks places, so there are companies who will do some evaluation in your house for leaks and fix that. And so most of our detectors were grown by what is called MBE, molecular beam epitaxy, or MOCVD, metal organic chemical vapor deposition. So MBE is very accurate, very sharp interfaces, but cannot grow very thick material because it grows 1 micron per hour rate. So you cannot grow hundreds of microns. But MOCVD, you can grow much more thicker material, so it is much faster, but the interfaces are not very sharp. But both needs very high vacuum MBE particularly, and they are very expensive systems. And because of that, that is the reason where this electronics, when they gets introduced, very costly. So this is a silicon wafer, and now Intel and other big companies, AMD or Intel, make silicon wafers like 12 inches or even larger. So, but the detector size is very small, and we can come up with large number of devices once you perform all the experiments first and get the device to work right. So initially the cost to process a device is $20,000 or something, even a 3-inch wafer. And growth also takes time and all that, so it is very costly. But the device can be like 25 micron or 100 micron by 100 micron. So you can imagine how many devices you can get out of a 12-inch wafer when it works. So that is why Intel can charge some price upfront until a competitor comes up with some other devices. But as soon as a competitor comes up with something else, they can reduce the price, because in the very first few wafers, they would make all their money. But after that, it is profit. So this is a list of our recent papers in different areas. This is the detector papers and nanostructure based devices, dots and wells and all that. So this is the new application part, the minimally invasive device publications. So if you are interested, you can go to the website and download the papers, PDF attachments there. And this is just a typical detector architecture. We start with the substrate. You have a bottom contact and layers, emitters and barrier layers, and a top contact and a metal. So the contact region is highly doped because otherwise you cannot get a good ohmic contact. So the light comes through here, and this is the different types of emitters. So you can have quantum wells, dots, other heterojunctions, any other type of emitter, same structure can work. And we have used this similar structure for all of our devices. This is a quantum dot structure grown by Pala Bhattacharya's group in Michigan. So this is the size scale. So you can see this is like 20 nanometers here. And this is a device which we have used with structures which has different sizes, 260 by 260 micron optical area. Electrical area is little larger, 400. So in one chip carrier, we have several devices because we want to check for the leakage, edge leakages. So then we can check whether there is any leakage from the edges when we have different area mesas in that. And you can see the scale of this using here. And if you anneal the quantum dots, you can get what is called a quantum ring. And so this is a quantum ring. The reason for annealing is to get a quantum ring. Quantum dot is a self-assemble. So that is, there is not much control in quantum dot size. And the size of the dot matters to have the energy levels. So the energy levels cannot be adjusted easily in a quantum dot. That means you cannot change the photon energy needed for the absorption. That in turn says that your infrared detector will have some specific wavelength. So if you want to change the wavelength, one option is you can change the size by converting the dot into a ring. Then you can extend the wavelength to longer wavelength. And there is another option by using a dot in the well, putting a dot inside a well. We can get to that in a minute. So this is a device structure, heterojunction, emitter and barrier. So I'm only showing the one band of that. So this is what is called the inter-subband or interband. When you apply bias voltage, so this is zero bias, flat. And if you apply bias voltage, bias drop is across the barrier because it is not doped. So now if you send infrared, the carriers will absorb the infrared photon and go through, and that gives you a current. So this is a photocurrent coming through because of infrared. So that is a detector. This is N-type, but this can be used for P-type too. So we have added this and extended that to a UVIR dual band detector, where we use both interband and intraband. Interband, this is intraband or inter-subband. So that is inside one band. This is what I was showing you just before, coming through just in one band. But the normal detectors earlier was going from one band to the other band. That is interband. So if you use gallium nitride, aluminum gallium nitride, you can detect both infrared and UV in the same device. So this is something we have developed for Air Force, and we have a patent and all that for this type of detectors too. So this is a structure for that. We have modified our earlier diagram to have 3 terminals to detect this infrared and UV. So the top 2 gives you UV response, bottom 2 gives you the IR response. So this is the response for UV active region. And when both UV and IR is there, the signal is almost the same. So this is the infrared response. For infrared, ignore this axis because we use the CO2 laser, which is just 10 micron wavelength. So the red is infrared active region, and when you just send UV, there is no infrared signal. So you see that light here, no signal, except this peak. This is an exciton in the nitride, gallium nitride. So everybody knows that. So that was still there in this one as a small feature here. But if you have both in UV and IR, you can still see the response in the IR region. So you can detect separately and simultaneously UV and IR. That means you can tell whether it is just UV, just IR, or both. And why UVIR is useful? When something burns, it emits both UV and IR. So this is the emission. So if you know the emission UV and IR together, then you can decide what is being burned. So that is what a firefighter needs to know, the origin of the flame. So that is, then they can decide how they can extinguish the flame. So the same thing is true for the soldiers. And if you are using a gun, the gun has a muzzle flash, which is like a fire flame. So that emits infrared and UV. So the soldier who has a UV IR camera can detect what the enemy is using for the gun. So checking the muzzle flash of the enemy you can find out what is the gun he or she is using, so you can move backwards or forwards. Landmine detection. If you are digging for landmines, the enemy will be dig 100 places and put 10 landmines in that. So if you are looking for the disturbed dirt, there are 100 places. How do you decide which one has a landmine or not? So you can use two different infrared bands, and because there is a metal underneath, the emissivity changes. So when you fuse the images from two infrared bands, you can clearly see the difference when there is a band, the landmine or not. This is a metal grating which we have developed to detect polarization. So the light, polarized light selectivity. So different the grids, the width and the distance between the grids and the width of each of the grid can change the polarization factor and also the height. So this is some response for S polarized light and P polarized for this particular parameters at 8.4 micron. And we were trying to develop 5 and 8, 3 to 5 and 8 to 14 region, both the atmospheric windows polarized light. So this is the extinction ratio for that. This is that 3 to 5 range. And again, this is some project we did for Air Force. And you might ask, why do you need polarized light? So this is an image of visible light picture taken from some height. So there are some trees. Carefully see this image. This is the same image with infrared. And now I'm going to show you the same image with the polarized light. Now you can see the importance of polarized light. Polarized light is used to detect sharp edges, and the nature does not make sharp edges. Only man-made objects have sharp edges. So now the tree, under the tree there are vehicles parked, so the polarized light clearly shows the sharp edges of that. So that is the reason for polarized light. Now I'm going to show you some terahertz images applications. Terahertz is far infrared, that is longer wavelength, but the frequency is on the other end, lower frequency. So this is a gentleman going to office with a paper in hand, visible light picture. Same picture with terahertz. You have a knife inside the paper and some gun and some other explosives and other things in that. So you can see, you may have seen the going through the airport, you have to remove the shoes because of the shoe bomber. And this is the visible picture of the shoe and a terahertz image of the same shoe. Obviously, if you remove the sole of the shoe, you can see that too, but that is not something you want to do every time you go through the airport. So this is a picture of a red pepper. You can see the seeds inside. This is this region of this, and if you go and look at a picture of a credit card or a bank note, this is Australian $50 bank note, the water image, and a credit card of this Professor Lewis from this Wollongong University. And this is visible, this is broadband terahertz, this is 2.5 terahertz. You can clearly see the chip inside and the details of the chip. So we have used our heterojunction detector, which I showed you before, for terahertz also. This is different aluminum fraction. If you change the aluminum fraction, you can get different wavelengths. So this is in the terahertz wavelength region with different aluminum fraction. So this is, I'm showing you 3 different curves. Since we don't have much time, I'm going very fast. So changing the aluminum fraction, you can change the wavelength. So this is a P-type aluminum fraction gallium arsenide emitter, and this is N-type gallium arsenide emitter, and this is aluminum gallium arsenide emitter with P-type. So if you are interested in getting more details, you can look at this paper and see how we did that. And I mentioned to you about changing the dots, energy levels using dots. So this is a quantum dot. You cannot change the size of this dot because the width cannot be changed because because of the self-assembly. So if you put the dot inside a well, now the transitions are coming to one of the levels in the well. So that is energy level differences. So let me jump to different detector. When we were using our earlier detector, we were trying to get some army funding. We tried hard to see what can we do to impress the army, and army wanted us to send our detector sample. So I told my students to measure the whole range. We were trying to develop 10 micron those days, but I said, let's measure from 2 micron. This is what we saw. We saw a peak which we were not expecting for free carrier. Earlier we were saying the absorption is due to free carrier, but this is unexpected result. And it is not free carrier, which goes as lambda squared. So we realized that because this is p-type, this is a split of energy. And that was very strong compared to the free carrier. So this is the full range of that detector. Free carrier part is here. This is the split off. And so this is the split off mechanism, how it works. The heavy hole, light hole, and split off band. And this is, we came up with the structure to detect with room temperature, this 3 to 5 micron range here, room temperature detector. So this is an unexpected result. We got funding and we got a patent for this also to develop a room temperature 3 to 5 detector. Then we were trying to improve the performance of this detector. So the standard detector was something like this, p-type, the emitter and barrier. So this is what we were expecting the result. So when we apply bias and send light, we get carriers through and get this response. So, but one of my students, and who was another postdoc afterwards, I asked him to come up with a model to improve the performance. So he came up with a model saying we need to have a graded barrier and an offset. So this is the offset, this is the graded barrier, and this is what we saw when we did this measurement. This is the expected result, 3 micron around that, but this is the result we got, which is very long wavelength. So you can see the image here. So this is the setup. So what we did was, let's say, try to block, put a cut-on filter, 1.05. So anything below 1.05 will not be there, but above 1.05 will be there. The response came down. And this is that it is coming down to 20 micron or so response. Now if we have up to 3.6, send only above 3.6. Now it is even more reduced. Now if you block further, block everything below 4.5. So that is the initial short wavelength light is not there. Now the response is very weak. But now when we send light outside, not from the FTIR, back again, we get the signal back. So this tells us that we need the incoming short wavelength to get to the long wavelength. So this is one way to detect far infrared without changing the energy gap, because the standard measurement technique for infrared detector is energy gap determines the wavelength threshold. The shorter the energy gap, you can go to longer wavelength. But when you reduce the energy gap, thermal effects come into play. So your dark current is high. So you need to cool it down. So we came up with the option to say, how can we avoid that? So this method avoids the threshold limitation due to the reduction of energy gap. Energy gap is much higher, which is matching 3 micron, but we can get to very long wavelength micron. In fact, we measured the dark current and fitted that, and so this work is published on Nature Photonics, and in fact, in the cover, they highlighted our work and also had a discussion with the editor on that. So this is something what we called as a hot hole detector, extending the threshold beyond the standard threshold. Again, this is unexpected result. And in fact, Divya worked on some of this work. And now let me finish with showing some results on the disease detection. So the idea is to use a blood test to detect diseases. So the very first time we tried virus-affected cells. So one of our colleagues were using various different viruses. So she gave us a cell which is affected by a virus, but she can change the virus, so the virus is inactive now. It is affected by the virus, but it is not going to harm anybody using that. So we did the infrared absorption. First, we did direct absorption going through, but we could not get any result out of that. So after that, we used what is called the ATR-FTIR, attenuated total reflection, because then we can control the penetration depth. You can control the penetration depth by adjusting the refractive index, wavelength, and the incident angle. So if you put a blood drop here onto the prism in the ATR crystal, so the prism is the ATR crystal. So the blood drop is what we want to measure the material. So we cannot change the refractive index of the blood drop, but we can change the crystal. So penetration depth can be changed. So if you check the unactivated cell and activated cell, we can see some differences between the two. So if you do statistical analysis on these differences, you can see whether there is a significance between these two. And by doing that, we identified the different energy values where there shows a difference between these two cells. So this one also, we have a patent on this one. So we could identify the virus affected cell after 15 minutes of the exposure to the virus. So at the time, the time scale was like 8 hours. The other biological techniques took 8 hours to detect that, and we could detect it after 15 minutes. So now, more recently, we have extended this idea to use detect diseases like ulcerative colitis and cancer. So ulcerative colitis is ulcers in the GI tract. And so in US, if you are 50 years of age or more, they recommend people to go and get a colonoscopy done. But people don't like to get a colonoscopy done, so people don't go there for that test because it is very uncomfortable. You have to prepare for one whole day, expensive, can have some side effects because you send a needle type sharp camera into your GI tract, and that can perforate your GI tract. So these can lead to colon cancer and other cancers. So what we said is we can detect this with a blood test. So this is our paper which came to the Biophotonics Journal of Biophotonics cover. And so this is that one paper, Biomedical Optics, and this is the Biophotonics cover, and also we have a patent application pending on that. And we have done some cancer diagnostics, initially worked with mice serum, where in the mice serum, we test the disease and control. And the same thing we have done now with human ulcerative colitis and also breast cancer. And let me finish the talk with showing two more slides. So this is the ulcerative colitis curves. Red curve is the mice after colitis. So DSS means mice were fed with water with a chemical called DSS dissolved. So when you drink DSS water, the mice gets ulcerative colitis. So our biology people confirm the mice has ulcerative colitis. So that is, we know that after the mice drinks 2 weeks of DSS water, they get colitis. And we have tested colitis mice and non-colitis. So that is the other blue is the mice who is drinking just pure water, not DSS. So you can see that the absorption curve, there is a clear difference. If you have the average of that, that is making it even clear. So now if you look at these peaks, we can fit these to biochemicals. So we know that this is mannose and glucose. And so now this, just because mannose and glucose has a difference, we cannot tell it is colitis. It can be some other disease. So to indicate that, we also tried metabolic syndrome, that is like diabetics, arthritis. So you can see this table saying that you can identify colitis versus arthritis and metabolic syndrome using these two. And also the arthritis has another peak in this region, which is not in the other ones, that is thymine. So this thymine peak is there in arthritis, which is not in the other two. So now we can also fit this absorption curve with the Gaussian oscillators, which we have fitted with 18 absorbers for that. So if you are interested, you can look at some of our papers, very recent papers, which tells you all the details. And maybe if I get a chance to talk to you later sometime, I can give you more details on those. So thank you for listening.
Yeah, thank you, Professor Perera, for such a nice and mesmerizing talk. And of course, we'll have a lot of opportunity now to knock you. And you are mostly welcome to come to Varanasi to have an interaction to us and give us a physical talk on behalf of IEEE Photonics Society. So anyway, and thank you so much for such a nice, excellent presentation. And I would like to invite some questions. I know the audience have a lot of questions. So let's see if somebody would like to say, ask some question. And I already have so many questions in chat box. So let me speak this out later on. First, let's see if somebody would like to interact directly to Professor Perera and ask some question.
Yeah. Yeah, thank you, Santanu. Yeah, I'm happy to answer questions.
Yes, audience, please turn on your microphone and start asking questions one by one.
Okay, Professor Perera, may I open?
Yes, sure.
Dr. Bhattacharya.
Yeah, actually, I probably in your, can you please go to your slide number 21?
Can you see this?
So, yeah, slide number 21. I believe 21 or 22, something like that.
This one or this one?
Yes, it's on slide 21, yeah, 21, yeah. So what I was just asking, so in this case, that if the identification has been done of simultaneously for UV and IR radiation, my question is that, is it polarization dependent? Means if I have the normal incidence with, you know, that with you know, that electric field along X direction and wave is propagating along Z direction. And another case, if I am having the electric field oriented along Y direction, but still the wave is propagating along Z direction, will it be feasible that you are having the two different types of response or identical response?
Not in this case. So if you are having quantum wells,
Okay.
That is going to have that effect. So the normal incidence will not work unless you have a grating or some other technique to couple for
Okay.
N-type quantum wells and all that. But for not this, this is not quantized states. So this one, we have tested polarization sensitivity. There is a very small polarization sensitivity, but
Okay.
not like quantum wells. So it is negligible in this case.
Okay.
But that is not coming from any quantized states.
Okay. Okay. Thank you.
Yeah. So the polarization part I told you is a separate one. So if you put that grid up of this, then it will be polarized. Polarization sensitive.
Okay. Okay.
Okay. So, any more questions, please, audience?
Sir, what are the sizes of quantum dots that we considered?
So the quantum dots were like 20 nanometer diameter, or the width is like 20 nanometers. So the curve I showed you, there was a bar which is 5 nanometers. So like 4 times of that will be the full width.
Okay. So they have been grown by the MB or MOCVD?
No, MB. They were grown by Professor Bhattacharya, Palab Bhattacharya's group from Michigan.
Michigan.
And in fact, I had another Indian postdoc. I think Jit might remember. I forgot his name right now. He did a calculation on the variation of dot size effects. So that paper should be in our website. So these different groups, their dots are different, and also it is. It depends on the growth conditions because it is self-assembled, not that very controlled. So each dot will be little different size, not exactly. So there is a distribution. So that paper is talking about the distribution.
So I mean, there must be some histogram, no? Particle histogram, from which you can.
Yes. In that paper, we looked at some of other experimental measurements people have done and tried to fit and say what is that difference coming in with that.
Actually, we don't have any MB in India. I mean, only 7 places are there, or nowhere they are functional.
Oh, no. IIT Mumbai, in fact, Chakravarti, he was a postdoc at Palab's group. So he
7 places are there. MBE techniques in India in 7 places are there, but I mean they are very conservative, and they in India, you know that they don't want to share with anyone. This is the problem because it is highly expensive also.
Oh yeah, I mean I can understand that it's highly expensive. That's true, but yeah. I think I have. In fact, so I think when we were working with Palab, Dr. Chakravarti was a postdoc there, but then he went to IIT Mumbai and got a faculty position. And after he went there, at the initial times, he sent us his samples for us to measure. But then I think I saw some of his papers where they are doing all the measurements now.
What kinds of terahertz sources you are using for measurements?
Oh, so we were using the black body source, and we also have a mercury lamp.
Okay. So that is true also at the low temperature measurements. That is 4K helium.
Yes, we did close to 4K, but quantum dot terahertz. I didn't show that quantum ring and all that. We had another tunnel quantum dot structure terahertz, which was much higher temperature. Not really 4K, but around 180, something like that.
Okay. I am mostly using the colloidal quantum dots actually.
Oh, okay. Yeah, we did some colloidal quantum dots UVIR dual band detector. Again, I think, I don't know, were you there when Viraj was around?
No.
No. So that Viraj is the one who did those work with Professor Tennakoon, who was the director at IFS. He was in my lab those days in the summer and all that. So the colloidal quantum dots was issue with stability, and it was even harder to get any size dependence, much harder than even MBE. So very different sizes and all that. So
yeah, that is some kinds of are there, but we can we have optimized. Even we have synthesized ZNO quantum dots up to 2.5 nanometer size, and
what
even
material?
ZNO quantum dots, zinc oxide quantum dots.
Zinc oxide. Okay.
Yeah,
Okay.
CDSE quantum dots also around 3 nanometer or even less than that also we have synthesized, and lead sulfide and many other quantum dots we have synthesized in the lab itself.
Oh, in fact, we did both this lead sulfide and zinc oxide for UVIR.
For the UV applications mainly.
Yeah.
And some kinds of graphene and some other materials also by MOS2, etc. We can also and some we have also, yeah, Santanu is having also some kinds of CVD also he is having, and he has also grown some graphene and MOS2. So some kinds of collaborative research we are doing here also, but because it depends on the facility wise, actually you have to.
Yeah. So, sir, Professor Ji, do you have more questions?
No, I don't have anything.
Yeah,
I am very much familiar with the lab. I am continuously watching what are the publications are there.
Okay, so we have so many questions in the chat box. So, Professor Perera, with your due permission, can I read it out?
Yes.
Okay, so Mr. Nilokpal is asking, what is the basic difference between an IR detector and IR sensor?
No, there is no difference between the two. I mean, people use different wording. Yeah, I don't think I want to say that there is much difference. But you can have various different types of detectors. But I don't think there is a critical difference.
Yeah, okay. So the second, he asked already another question is, what is the structural difference between a thermal and photonic IR detector?
Photonic detector, there is quantized states. So there should be some dimension things. So it cannot be a structure which is very thick, wide regions. I mean, overall, you can get, so it is like a microstructure and nanostructure scale device, each device size. So if you have a quantum well, when you have a quantum well, if you go to basic quantum mechanics, you know the quantum well, right? Particle in a box, quantum well. So you have quantized energy states. So if you have quantized energy states, then the energy transfer is from one energy level to the other level. But then if you increase that structure, the energy state is going to be the energy levels are going to get closer and closer and make a band, energy band. And then it is still can be free carrier absorption. So that is still electronic transition. But if you don't have that free carrier part and energy levels, then you absorb the energy into the material and the whole material temperature has to change. If the whole material temperature has to change, when you change the temperature of the material, the resistance of the material change. So when you, let's say you have applied a bias voltage and the resistance changes, your current changes. So that is how the thermal detector detects infrared, and that is how we know that the thermal detector is detecting infrared, because enough heat is absorbed and the whole material, the temperature of the whole material has changed, and that changes the current, and then you know, okay, there is some absorption. But in the other quantum type device, whether it is an energy level or a transition like free carrier from one energy to the outside level, that is electronic transition, either electron or hole, which absorbs very quickly. Maybe it might need a four non part or not. If no phonons, it is extremely fast. If there is a phonon, it is little slower, but much faster than the thermal part. So that is the difference between the two. In a photon detector, you don't need the heat. You don't need to heat the whole structure.
Okay, sir, thank you so much. So another question from Mr. Ghosh, Sambit Kumar Ghosh. He is asking, like, what are the suitable materials for useful for terahertz detector applications? Is graphene can be used for terahertz detector application for an efficient performance?
Graphene is used as good for anything and everything. But that was the case is quantum dots, and every time something new comes up, it is the case. So the I think it is the responsibility of scientists not to promise things which is not really the truth, and also produce things before they say that this is done. So graphene people are trying, yes. So I don't want to say that no, graphene cannot do that. But the graphene, if you can get the energy levels to be very close, and also people are talking about zero energy levels, so in theory it is possible, but in practice I don't know how good that is going to be. So there are so many different. So the bottom line is, for terahertz, you need to have terahertz absorption to get the detector. So either it should be, in fact, then the microbolometers are reasonably far. So it is micro. The size of the structure is a microstructure. So even though you need to heat up the whole material, the material amount is pretty low, small. So it can change the resistance pretty quickly. So there are microbolometers and MEMS. People are trying various MEMS ideas to use for terahertz. So there are various different types of that. But what we were trying to do is to say, our main goal was, we don't have materials growth, and most of the thinking is you want to develop a new material for various different applications. For 5 microns, one material, 8 microns, another material, 10 microns, another material. So that means every material you need to spend a lot of time and money. So in research point of view, if you have an MB machine and you need to find money to maintain the MB machine, so you need to ask for more money to come up with and promise very good materials and saying this material is great. We need too much money. That is the different aspect. We don't have that capability. What we were saying is, gallium arsenide is very well developed material. Everybody has putting money into this and developed it. Nobody complains about the material. We are going to use gallium arsenide to detect visible, infrared, UVIR, dual band, polarization sensitive, terahertz, everything.
Everything, yeah.
So we are saying,
even sir,
we are
it
not
depends on actually what kinds of mechanism is involved in the terahertz detection. Because
say,
for
say
it,
that again.
it depends on that what kinds of mechanism is involved in the terahertz detection. So material actually that is for your device, that is interfacial work function. So there basically that is many body effects are involved.
Yes.
So So in that case, actually, the gallium arsenide, aluminum gallium arsenide, again, I mean, that is well-established materials actually that we have seen mostly.
Yeah,
But
that is what I'm saying. That if we can improve, so the thing is, we are basic physics people. So
Yeah, yeah.
we want to come up with physics principle and say that we can detect this.
Yes.
So we have shown that. But the issue is how can we improve the performance to match the best available performance.
so,
That is
I'm sorry to interrupt, but actually, I was just thinking to ask you the question regarding that aluminum gallium arsenide and gallium arsenide, whatever you are talking about.
yes.
Oh, no, they are the, you know, they are the basically a magic material. They're super. But for improving performance, I believe the interface, you know, the interface matters a lot.
Yes.
Because the semiconductor and electrodes, there is some sort of defects and some sort of heterostructure, which basically create a barrier.
No, Dr. Santanu,
Yes.
actually, gallium arsenide and aluminum gallium arsenide, there is a very good matching. Lattice mismatching is very, very
No,
minimum.
I'm not. No, I'm not talking about the both the semiconductor. I'm talking about the semiconductor and metal, like electrodes.
No,
When
Yeah,
interface
that is why I was specifically saying the contact region is highly doped.
yeah,
So if your contact doped is highly doped, you can get a very good ohmic contact,
ohmic
and
contact.
that is
Yeah.
also very very well developed. So the problem comes if you have a Schottky contact.
yeah, that's
Yeah.
what my question
Is
was.
what you are saying.
Like
Schottky
if you
contact.
have
That is
some sort
not
of
the
barrier,
problem in the field. It is not an issue. But for gallium nitride and other materials, it was an issue. P-type contact is the
Yeah,
issue.
yeah.
I see.
But for gallium nitride, nobody in the right mind says there is a problem to make a good contact. That is already solved.
Yes.
So it's mostly for gallium nitride
No,
and
no,
other kind of nitrides.
no, no.
Right?
In general, whenever the band gap of the material is increased, then certainly to get a ohmic contact is very, very difficult. So gallium nitride is having energy band gap is around 3.37, whereas gallium arsenide is 1.42. So to get a ohmic contact in gallium arsenide is very easy. I mean, it is well established techniques are there. But to
No.
get that one in the gallium nitride is somehow difficult.
Whatever
Gallium
I
nitride, another problem is that I mean, N-type gallium nitride also is difficult to achieve.
it is not only band gap, probably work function as well. So
Which one?
Yeah.
work function of that semiconductor as well.
No,
So
work function actually for any contact, actually you know that whenever a ohmic contact is made, the work function of the metal must be larger than the work
yeah,
function of the
that
semiconductor.
is quite a common
Okay, so
practice.
this is the basic theory. This is the basic theory. But in addition to that also, I mean that does not guarantee always that you will get a good contact. Many cases of the pinning of the Fermi level, that also matters. So I mean, gallium nitride has a lot of problems, but gallium arsenide is a well-established materials. And
Okay.
But
the mismatching between
just to
gallium
add
arsenide,
to that, just to add to what Jit is saying, yes, gallium nitride has much more problems than gallium arsenide.
yes,
But even gallium nitride, now people can make contacts, and gallium nitride LEDs are there and all that. So it is much harder. So it is little bit more costlier and all that.
Yes,
But gallium arsenide, there is no issue. Nobody talks about any problem with the contacts for gallium arsenide or LEDs. Gallium nitride, until very recently, P-type contacts were really hard. But now that is possible too because they have LEDs now, working LEDs.
yes, yes.
And mostly whatever you like, you know, put a perspective like how to improve the performance. So in case we would like to improve the performance, then first and foremost the important thing is probably the interface, like whatever I'm trying to say. Is that the one or something else is
no defects are I mean interface is important too.
Yeah.
But the interface if you are so that is where the MOCVD and MBE comes into play. Interface is not very sharp if it is MOCVD. So then you cannot get the separation. So there is a tail going. So if you want aluminum gallium nitride some region as the barrier and a gallium nitride region as the emitter, and you want a very sharp interface, okay? and if the interface is not very sharp, there is a space charge effect.
Yes.
So then the barrier is going to get into the other material. So the barrier, when you apply a bias, the space charge is going to change things, and it is not what you have designed. So the energy gap is not going to be that same value. And so, in fact, we started, I did not say anything, first using what we call homojunctions, where we use gallium arsenide, just gallium arsenide, doped an interface.
Yes.
And I think maybe JIT, when you first came, you worked on something along this line with, in our lab.
So,
And,
sir, when you were talking about some defects, so what kind of defects you are talking about? Is that processing defects, or that semiconductor do have some other defects as well?
No, the detector performance doesn't care what type of defect is. If there is any defect, it is going to affect the performance. So, but the processing defects now can be controlled very well for gallium arsenide. So processing part, I mean, if you are going to have annealing when you are trying to make the contact, if you are going to do diffusion, obviously there is going to be a problem because you cannot control very much.
That's true.
So it is a issue between the cost and what you want. If you want to get it done very cheaply, yes, then you have to live with that. You cannot control the penetration. But if you are bombarding with that, then you are going to damage the material.
Oh.
So that is another problem. But
all right. So thank you so much.
If you don't have issue with the money and you have all the facilities, there is no problem with making without problem.
Sir, in general, MB gives very good contact interface. Very good quality of interface is given by the MBE method, and there is no problem. Second thing, I'm just telling you, the interface effects. I mean, basically lattice mismatching, and due to the thermal difference in thermal expansion coefficients. So particularly gallium arsenide, aluminum gallium arsenide, they are very much well matched. So these are the, I mean, widely used material, I think so, for the photo detection applications, particularly for the quips. Gas and
so
algae.
The issue is there in quantum dots and things like that, because it is self-assembled. That means they need to have the strain. It is mismatched. So if you remove the mismatch, there won't be a quantum dot. So in itself, there is the mismatch. So that mismatch means there can be a lot of problems. And if you have gallium nitride, aluminum gallium nitride, there is a lot of defects in that growth.
A lot of defects are there. Yes.
Even now, although they have LEDs and all that, still the gallium nitride, gallium nitride and all that, there are various defects.
Lot of defects are there. Even if you go through for the HEMT, high electron mobility transistors, you will even get a negative conduction region also there in the due to the defects. I mean, the trap centers are there. They can capture the carriers also in the gallium nitride. So gallium nitride, they are used for various purposes, LEDs and for many other purposes. But gallium nitride has many problems. But gallium arsenide is well established and very good material.
Okay, so sir, our next question is like, is this technique virus infection detection limited to some specific disease, or we can detect any kind of virus detection? If yes, detect coronavirus. A good question.
So why virus detection itself is okay. I guess maybe somebody is thinking about COVID.
Yeah, that's what. But that's a good question. I like the question actually.
Yeah. In fact, so the cell. The question asked about in the cell. So I will separate that into the first one and the blood serum. So in the blood serum things, we are not separating cells. But in the earlier curve I showed you, very first one, it was cells. So the cells, in fact, my student, the one who is almost ready to leave because as a postdoc from next month, was telling me about a year ago when the COVID came, let's test for COVID. But I was thinking about that and decided that maybe we might not get the COVID because COVID is connected with the ear, nose, throat, the respiratory system. It does not get into the blood directly, quickly. So to get to the blood, it takes time. So we will be able to probably detect that, but that is the antibodies. If there are antibodies, they are in the blood, and then it is probably we can identify some changes in the composition. So it is possible to do that based on that, but not as quickly as other PCR or some other testing because it will not get to the blood quickly.
That's very interesting part of this virus things actually.
Yeah, but to detect other diseases, so what we have shown is we have shown breast cancer, melanoma, lymphoma, ulcerative colitis, arthritis, metabolic syndrome. So I think that this theoretically can be extended to a lot of other diseases too, as long because any disease, see, the blood has lot of different chemicals. So I mentioned that we have identified about 20 chemicals in the blood with the absorption. But that does not mean that it has only 20. That means that our absorption is coming mainly from those 20 components because we have limited the penetration depth. Because when we send the light completely through the blood sample, we get so much results, we cannot understand that. It is too much. So we moved away from transmission and said ATR, limit the penetration depth. So we can reduce the absorption, so our information is limited to whatever amount we want. So now we can fit the absorption curve with 18 to 20 the Gaussian oscillators. And those Gaussian oscillators can be matched with biochemicals, which biology people and the FTIR people have already databases. They are saying that this wave number is amide 1, amide 2, or random coil, or alpha helix, beta helix, whatever else. So that I think that any disease will change your blood composition, some things. It is not going to be completely changing, but one will go up, other will come down. The idea is something like now diabetics. If you have diabetics, the common simple test is the blood sugar. If it is above 100, you have diabetes. If it is below 100, you are normal. If it is close to 100, you are borderline. So that type of chemical identification saying, okay, if you measure alpha helix, beta sheet, if it is below 5, you are fine. But for different, so we have a table. I think in our recent paper, we have a table which have 19 different biomarkers saying that how in our 5 different diseases, which one changes. So yes, I think long term it should be possible. In fact, we need to do more because otherwise we cannot say that it is this disease. If we don't know, it is not that other disease.
So, sir, the next question is, how did you introduce quantum dots in quantum wells?
So that is when you use the materials growth part. You have, let's say, gallium arsenide. So you have gallium arsenide layer, and in the gallium arsenide layer, you put another layer which is lattice mismatch. I guess if MB Grover is here, he or she should be able to tell in much more details than that. But the lattice mismatch layer, indium gallium arsenide or something, that will form the quantum dots in that region. Then you put the aluminum gallium arsenide layer after that, then you will get the, so because earlier gallium arsenide was the well of the quantum well part. So then you put the in-gas layer to get the lattice mismatch. Then you put some more gallium arsenide, so you introduce the well. So the dot is in the middle of the well. Then you put the aluminum gallium arsenide layer that will make the barrier.
Okay, so sir, next question is, what role interface play in organic polymer / inorganic material?
I don't think I can answer that. I don't know too much about
Yeah,
polymer.
he has not worked with polymer.
Yeah, so the
I
question
have
is
not
related
done chemistry after my A levels, which was I had to do that. So I did that, but
inorganic
I think the
materials like
polymer.
N-type zinc oxide nanorod. So somebody are asking like why, like what is the role of interface in kind of inorganic material like N-type zinc oxide nanorod?
So,
And
I think, I mean, okay. So having said that, saying I'm not qualified to answer that question, I can speculate. So any interface matters when you are trying to separate the two materials. So if the effect is you are looking for needs to have a clear separation, then your interface will play a role. Because then if they are mixing, what is the effect of mixing the two things? So that process, so let me ask, so the zinc oxide, what was the materials you were talking about? Zinc oxide nanorods and what?
yeah, zinc oxide nanorod, N-type zinc oxide nanorod.
And polymer.
So and a polymer. Okay, so the nanorods, so if you are trying to align the nanorods in some particular direction, if the property you are looking for depends on the alignment, if that is the case, and if it is there is no interface, the zinc oxide is going into the polymer also, so then your expected result will be weak. So definitely there is an effect. This is my speculation. I'm not an expert on that. I mean, I don't know too much of growth either, but and nothing about polymer. But I think there will be something, but it depends on what your purpose is. What are you looking for?
Okay, so sir, next question is, what are the specific biomarkers presented in human blood? Is there any specific biomarker for different kind of cancers?
Yes, we have identified. So when you say biomarkers, we call it spectral marker. Okay, because the nomenclature is different from the biology people call biomarkers, which are different from what we call. So they have biomarkers like different genes and other things. So, but what we are saying is spectral markers where we get in the blood. So if you look at my website, go to the website under publications, and you can download some recent papers on that cancer. So we have 2 papers on cancer. One is on mice, melanoma and lymphoma, and the other is breast cancer. So there we have about 18 spectral markers. So one is alpha helix to beta sheet. So I mentioned before that we can identify these spectral markers in the blood serum absorption curve. So that glucose is one place, mannose is another place. So when we have a peak in that particular point, we say that peak comes due to glucose or mannose. So glucose is a spectral marker for us. Mannose is a spectral marker for us. Alpha helix to beta sheet ratio is 1. So like that, we have about 18-20 markers. Maybe I may have some. Let's see whether I can get to the slide and whether I have anything in this one. If you want, I can show you one curve using a different slide which I have. Yeah, let me try to show you a different. I think I can close this file now, right? Can you see the screen now?
Yeah. Yes, sir. We can see it.
So this one, can you see this slide? Side chain, beta sheet, random coil, alpha helix, beta turn, beta sheet.
Yes, sir.
Okay, so this is one of the there are six spectral markers. So this is absorption curve. So that absorption curve, and that was fitted with these six biochemicals. So these six biochemicals are biomarkers in our case. So in biology, that is different. In biology, what they call biomarker. So then you might ask, why do you want to do this? And biology people do biomarkers like that. Okay. What we are saying is this is a blood test. This is not a very detailed, costly biopsy or very invasive technique. And people don't worry about giving giving blood. When you go to the doctor, maybe you give your finger prick and take blood. That type of a blood drop is enough for this. We use only 1 microliter. So this can be done easily and checked for early detection. If you are looking for breast cancer, to get the biomarkers, they need to do a biopsy and take piece of your body and go through all that, and a week later you get the result. And unless you feel some problem, nobody wants to go and get that type of invasive technique. But people don't worry about going to give a little bit of blood. So that is the reason we are saying this is a better technique. We can do this quickly and not very costly either.
Okay, so sir, next question is, can we increase the detectivity or responsivity of IR detector by using lanthanide materials?
You cannot put the lanthanide material into the gallium arsenide and improve the responsivity or detectivity. But lanthanide material itself, I don't know the absorption properties of lanthanide, whatever specific lanthanide. So if you can have the energy gap matching the incoming photon of the IR detection you want, yes, you can use that as a detector. So the responsivity or detectivity will depend on the noise also. So whether you can get a very high quality material. So if there are a lot of defects, then the detectivity is not going to be high. And for responsivity, you need to have good absorption. So if you have very good absorption in that particular lanthanide material, yes, you can improve the responsivity, but you need to worry about the dark current. So can you reduce the dark current to improve the detectivity? So I cannot tell you yes or no, but you have to work that out using the basic physics principles to see whether it is possible or not. But if lanthanide is known to have very good material Colitis, yes, you have a good chance. That particular lanthanide.
All right, so we had a lot of questions, and thank you to all the audience for their curiosity and asking too many questions. And I hope Professor Perera will not mind.
No,
And
that's
we
fine.
really enjoyed your talk, sir. So
Thank you.
first of all, thank you so much for taking your time and then come for this kind of distinguished lecture. And we really are very, very grateful for your kind, participation in this event. And I would also like to thanks Professor Jeet for coming here to be to have with us, and we had a lot of discussion. And from IEEE Photonics Society, I would like to thank you to all the participants, most of them from outside as well as the inside, like IIT BHU. And hopefully we will have a lot of more interaction in future. So if you have an opportunity to visit Varanasi, we'll be happy to be a host over here.
Thank you.
And thank you so much once again
Okay.
for delivering a lecture.
Okay. Nice
Okay,
seeing
thank
you.
you, sir.
Jit. Okay. Bye.
And thank you.